right, let's apply what we just did.
Okay, let's do it. I know exactly what 3 to the x looks like.
We actually just drew it like just a moment ago. So what does it look like?
A little cross the x-axis at 1 action there, and the y-axis at 1.
The y-axis
The y-axis at 1. We're going up z's on the right, down z's on the left, but not crossing the x-axis. So we're getting close, but not touching close. No, don't touch. Don't touch.
I didn't touch it.
Now we're going to go 3 to the x plus 4. Well, since we're actually messing with the actual x, that moves us horizontally. So instead of being where we're located, that where we cross that x-axis part will be moved to the left 4 units.
Because it's
of the
in the
plus
exponent,
4.
It's the opposite.
Yep,
of what
super
you think.
secret opposite
Shift left
society.
4. So this 0.01 needs to actually be over here now at -4. And then the rest of it is just, it's gone.
There you go. There it is, right there.
Up that way.
And there you go.
Okay, let's try another one.
Okay, let's do e to the x. E to the x is one of those naturally occurring numbers that some famous mathematician was able to get his name onto.
Yeah.
Euler.
Yeah, good guy.
Thinking of naming a number after myself called the Hazel Calc number.
Okay.
The number 1, because I'm number 1.
Good luck with that.
You don't think it'll work?
I don't think you'll get anybody to call it that. All
We'll
right.
see.
It still starts at 1 because we still have 1 times e to the x happening. Our initial value is still 1. And it's actually going to be really, really similar to 3.
In fact, you probably won't be able to tell a difference.
Because e, actually, if you type just e into your calculator, is 2.7.
2.7 something. It's like pi. It's a non-ending, non-repeating number.
Yeah.
So, hey, it looks...
Initially, it looks pretty similar.
Looks almost identical.
So let's do some transformations.
Negative e to the 2. You put, hey, there's 2 things in there.
There are 2 things. So what about inside of our exponent? What's that doing?
That's going to give us not a stretch, but a horizontal shrink
of
1/2, or by a factor of 2.
Horizontal shrink of 1/2, and the negative in front is a reflection.
It's going to reflect you over the x-axis. So if we have a horizontal shrink, we're squeezing it like this, which means it's going to grow like this.
Okay. So this 0.01 is going to be down here at halfway to 1, right?
Right.
Is that right?
I believe so, because...
No, it's a horizontal shrink. Horizontal means
left to right. No, so it still goes at 1.
So what happens at 0 stays.
What happens at 0 stays at 0.
And so, but then as we go to the left, we're still getting closer and closer and closer. And then as we go to the right, it actually is going to, every point is going to move halfway to the y-axis.
Right.
Right?
Right.
So it actually goes
grows
up faster.
quicker.
Because horizontal shrinks often look like vertical stretches.
That is correct.
So
often look that way.
So there you go.
All right. Good talk.